Okay, we're going to talk about common ion effect, which you guys have alluded to a couple times. So the basic principle is that in these previous problems, we were dissolving these solids into water, assuming that no other ion was present in those solutions, but now we are dissolving these compounds into solutions that already have one of the ions present or have something present that affects the solubility by changing pH, for example. So let's look at this one. So in this problem, we found the molar solubility of silver chloride in water, and we found that the KSP is really, really tiny. I mean, that was given, right? Now we're going to see how the molar solubility was still tiny. -37 is minuscule. Okay, so next we're going to see how that solubility would change if there was already chloride present in the solution. Okay, so if you want to do a rice table, you can, and I mean, you could just copy it if you wanted. I don't know if this is going to be easier. But the difference this time is that we're not starting with 0 of the chloride and the silver both. We're only starting with 0 of the silver. So we can tell from the question that we have 4 times 10 to the negative third molar calcium chloride. Because calcium chloride is CaCl2, the concentration of the chloride is actually double. And I hope that you understand why that is. So this is the value that we're plugging in for the initial concentration here. Okay, and then we're going to dissolve. In this case, X is going to represent a different value because less will dissolve when chloride is already present. But it is the molar solubility will be the answer for this problem, just like it was in the previous problem. Okay, so the difference here is that we're not going to have X chloride in water at the end. We're going to have 8.0 times 10 to the negative third plus X, but much like before, but especially so now, because this has such a low solubility, again, -73 is tiny, X compared to this quantity is very, very negligible. Okay, so our KSP expression will be the same as before, but now we're plugging in different values. So the KSP we were given up here, 1.6 times 10 to the negative 73. Our silver ion concentration, I guess I can just write X for that, will represent the molar solubility of silver chloride, again, because of the 1-to-1 molar ratio. And in this case, we're plugging in something other than X here. So we're not going to have X squared, we're going to have X times this. And our molar solubility will be 2.0 times 10 to the minus 71 molar. Okay, so if we compare, we can see that it's quite different and much smaller than we had up here, 10 to the negative 37, and that's because of the presence of one of the ions already in solution. So you can significantly limit the solubility of a substance if one of the ions is already present. Okay, so in summary, just like it says here, for the common ion effect, one of the ions is already present, and the change will be negligible, which is to say that we can ignore the minus X, right? It doesn't count. And ice tables are useful, but eventually you won't need them. Okay, so this is not qualitative, this is more conceptual. In which of the following solutions will PbOH2 have the lowest solubility? So just to kind of remind ourselves of what the math would look like on this, let's just write out the KSP expression, which would be this, okay? And I mean, just in order to allude to Le Chatelier, if we need to, we can also write this. Okay, so this is similar to the question about whether or not the pH at the equivalence point will be neutral, acidic, or basic, and that was hard for all of you guys, and I would say it's one of the hardest things that we talk about is like looking at a compound and thinking about the ions that are in it, and then understanding whether or not they're going to do anything with water, and in this case, whether or not they're going to do anything with the ions present in the compound that is in question. So it takes like a lot of understanding of all the different things at play. So it is okay if this takes a little bit of time to really register with you. The most important thing to think about is strong acids versus weak acids. whether or not they ever stay protonated, what their conjugate bases do. So let's kind of think about it from that perspective. So as a general rule, sodium does nothing in water ever with anything. Okay, chloride can form complex ions, which we'll talk about later, but again, chloride is the weak conjugate base of a strong acid. So chloride will not affect the pH of the water. We can see, because this compound has hydroxide in it, that it will be susceptible, like changes in pH will affect its solubility. But chloride will not affect the pH. It doesn't do anything with water. So the chloride and the hydroxide aren't going to get together. Obviously, the chloride and the lead. Let's see. I'm trying to think now if like the lead chloride solubility would matter. I don't think so. I'll come back to it if it does. I mean, what I'm thinking is like, oh gosh, I don't want to ruin this whole thing. I'm going to come back to that one. I'm asking myself now, like, if the lead and the chloride react, maybe that is what I was going for with this problem. The lead and the chloride react and form PbCl2, that would pull this out of solution, right? I'm going to come back to it. Okay, this one's more obvious. Okay, lead is already present in solution. Lead is already present in solution, so this will very much limit the solubility of a new compound that also has lead in it. Okay, just like we did in these previous problems up here. Okay, the nitrate is a weak conjugate base. It doesn't react with solution. It's not going to pull protons off of anything, so it doesn't really do anything. Okay. So in which of the following solutions will PbOH2 have the lowest solubility? It would have a low solubility in here. That's correct. Okay, and then 0.7 molar perchloric acid. This, as we know, is a strong acid and will dissociate completely. I mean, we'll just do it the Morgan way. We don't need that H or that water. We'll just do this. Okay, so as a result of this reaction happening, there's a bunch of H+ available, and we get a secondary reaction happening over here, which is the neutralization of the added base, which basically continually depletes the concentration or the presence of hydroxide ions, which enables more of the solid to dissolve. This is very similar to the magnesium hydroxide demo that we did, where we added acid, and then it got less and less cloudy over time because it was pulling hydroxide out of solution, which was then pulling this into solution. Okay, so for part C here, the solubility would increase. Okay, for this one, solubility would decrease. Okay, and I believe, actually, if we're really going to get into this, even though I still need to clarify it, the solubility for this one, if anything, would also increase, because when you have sodium chloride present in solution, the chloride will precipitate out with the lead according to this reaction, which, similar to how the bottom reaction will remove hydroxide from, or the presence of this here will remove hydroxide from solution, the presence of this here will remove lead from solution, and both of those will open up more space in the solution for additional PbOH2 to dissolve. So the answer for this would be definitively B. So A, I kind of stumbled on A myself. But hopefully that makes sense. If it doesn't, we can talk about it during the Zoom meeting. And at any rate, we understand that it would not lower the solubility of PbOH2. Okay, last slide for this. So this is similar, and this is conceptual. Which of the following substances will become more soluble at a lower pH? So that's H+ present. So write equations for the reactions that occur to increase solubility. Okay, so will H+ react with anything in PbI2? So Pb does not react with H+. Does I- react with H+? If it were to, it would make HI, which is a strong acid, right? And strong acids do not reform in solution. So I would say that this does not happen. So PbI2 is not going to have a change in solubility because of the presence of extra hydronium. Okay? So again, cation here is not going to react with H+, but can carbonate react with water or with H+? So this reaction would lead to the formation of bicarb, which we understand does happen and is actually product favored. Even if it wasn't product favored, if it happens to any extent, it will still pull carbonate out of solution and make more space for this to dissolve. So we would say that this one will become more soluble at a lower pH. Again, strontium's not going to do anything, but phosphate, again, like carbonate, is the strong conjugate base of a weak acid. And for both of these, because you could kind of protonate them more than once, there could be like successive protonations that take place, like this one all the way up to H2CO3, this one all the way up to phosphoric H3PO4. Okay, so this one also will become more soluble at lower pH. So the principle then here, like the summary is salts that contain anions that are the strong conjugate bases of weak acids will become more soluble in acidic solutions. Okay. This is the work that you have to do based on these slides. So 41 is asking about the solubility of iron 3 hydroxide in each of these solutions. This is a little bit confusingly phrased, a solution buffered at pH equals 5. So basically, when it's saying pH equals 5, it's giving you information to calculate the concentration of something that will relate to this compound. So think about it that way, and same with 11. Okay, for this one, this is just really similar to the silver chloride example. You already have phosphate present, so how will that affect the solubility? And this one is just a different perspective. You're given the solubility and then asked to find KSP. For all of these, you need to be careful with like exponents and also coefficients, like ratios between this and the whole compound, that sort of thing. Okay, and then lastly, this one will be helpful for you to think about pertaining to the last slide. Okay, and again, you're going to do these and then upload your work in one document to Veracross.